Okay guys, this is a video I'm really excited to make. This video is on related rates, which is just a name for derivatives application problems. So essentially we're taking our knowledge of derivatives and applying them to word problems. We're going to start with some really simple applications and then build up to some cooler ones. So if you read this text here, we're talking about the perimeter. We have a rectangle and we're talking about the change in the rate of the perimeter. So this is a geometry idea. So you've known how to kind of approach this problem since 10th grade, and we're just going to add some calculus in. The reason this is cool is because this is the first place in this class, really, where we're drawing conclusions using calculus about real-world things that we couldn't have drawn before we learned any calculus. Okay, so let's jump into it. We're going to use a method on every related rates problem, so every derivatives word problem, that is 4 steps. The first step is going to be, if you can, draw a sketch. So to draw a sketch, I'm going to read all the words. So a rectangle has a length of 11 inches and a width of 7 inches. And if you had this on paper, you would annotate, right? Whose sides are changing. So this is the calculus part, right? We're adding in this rectangle that's like growing or shrinking. The length is decreasing by 6 inches per second, and the width is shrinking at 5 inches per second. What is the rate of change of the perimeter? Okay, so that's my question. My sketch, we can just draw a rectangle. To be honest, we didn't really need to sketch this one because we know what a rectangle is, we know what a perimeter is, but it's a good habit to get into. And we'll go ahead and label our dimensions here. So 11 inches is my long side, 7 inches is the shorter side. And we want to know the rate of change of the perimeter. Okay. Well, our next step is going to be to write an equation. So often, in AP calculus at least, this is going to be a geometry equation, just because it's an easy thing for them to assess you on, right? So you guys already know what the perimeter of a rectangle is. So my equation in this case is going to be just my perimeter formula. 2 times the width plus 2 times the length, because perimeter is the distance around the rectangle. So I've written my equation. That's my second step. As we get more diverse problems, we're going to see more and more equations that we can apply this to. Then, actually before I give you step 3, I'm going to rewrite this equation in an interesting way. So because our rectangle is changing over time, we can rewrite this as a bunch of functions. We can say perimeter is a function of time, width is a function of time, length is a function of time, right? So all these things are in flux. This rectangle is like stretching out or shrinking, you can imagine that. So all of these things are a function of time. Now often, as we find in this section of calculus, our next step is to take the derivative, right? But more specifically, take the derivative with respect to time. And I'm going to add in here chain rule. So we're always going to think of this as a chain rule type of problem. So let's see what that looks like. So we have some function, perimeter of time. I'm going to write the derivative using this notation, dp over dt, just because I find that kids are more successful using that notation. Then the derivative of 2wt, well, that's a function, 2 of times something is just 2, and then whatever the derivative of the inside is, so dw dt is how I'm going to write that down. Then same thing, 2 dl dt. Okay. So I've taken my perimeter equation, I've taken the derivative of the entire thing with respect to time. Now, remember what I'm looking for is what is the rate of change of the perimeter? I'm going to substitute and solve. This is where it gets cool. So, we have our length is 11 inches, so that's plain old just L, right? We already found that when we drew our sketch. W is 7 inches. The length is decreasing by 6 inches per second, though. That's a derivative, right? That's the change in length over time. And it's decreasing, so it's going to be negative. Width is also shrinking. So dt is going to be negative 5. And then I just plug that in. So I have my two derivatives. I'm looking for dp dt, so I don't need to find that. That's what I'm trying to solve for. And I get 2 times negative 6 plus 2 times negative 5. And then I just simplify. So what, negative 12 plus negative 10 is negative 22. And this is a length, right? So this is, what are my units here? Inches per second. Okay. So this is a great time now to pause and just make sure you follow that. Make sure you capture these steps in your notes, and then make sure you capture this example. And then we're going to move on to a cooler one. So here, same text, so you can take a second to read it, pause if you need to. We have a rectangle that's 1 inch by 7 inches. And the sides are changing. The length is increasing by 10 inches per second, and the width is growing at 8 inches per second. What is the rate of change of the area this time? So we're going to sketch, we already did that. And then we're going to find our equation. And here, last time we used perimeter because it asked us about the perimeter. Here we're going to use area. So area is just length times width. Then we're going to take the derivative with respect to time. So here's where it's more useful to rewrite this as a set of functions. So a of t, L of t, and and w of t, right? Okay, because all of these things depend on time. So I'm going to say the derivative of a of t is dA dt. The derivative of L of t, well, hold up. So I'm multiplying here, right? So if I'm multiplying, I need to use the product rule. So I'll say L of t times dw dt plus w of t times dl dt. So that was product rule because it's f times g prime plus g times f prime, right? So because I'm differentiating with respect to t, and because these are all functions, I need to treat them like that, which means when I take my derivative, I follow the rules. So usually it's chain rule, product rule, one of those. I always think of these as chain rule because these are still functions with respect to t. So there is my equation, and then here is my set of derivatives. This is called the differential equation. And then I just substitute again. Here it looks a little bit different. So L of t, so we need to go across, right? So dA dt is again what we're trying to find. Then L of t is my length. So L is 1. So this becomes 1 because this is just my plain old length at this particular time. dw dt, well, that's the rate of change of the width. So the width is growing at 8 inches per second. So that's dw dt. So times 8 plus w of t, well, that's just my width. So that is 7 times dl dt. The length is increasing at 10 inches per second. dl dt is 10. And then again, I just simplify. So 1 times 8 plus 7 times 10 is 78. And here we're dealing with an area, right? So the area is going to be inches squared per second is my dA dt. So for this assignment, you're only going to see these two problems, these two types of problems. So either you're finding the area or the perimeter, so you don't have to think too hard about that equation step. Really, this is just practice in setting them up and solving them in this particular way.